All right, so first we'll discuss about pandas or pandas. After that, we'll have a discussion on like the confusions that you've been having about the assignments, the groups, etc. Again, you don't need laptops today. So we want to start off with where we left in the previous class with numpy. We want to look at a few things which numpy is very good at, but a few things where other tools like pandas or pandas are better suited. And we'll see some of the other functionality. I'll, again, like previous lecture, I will do a few imports, numpy, pandas, matplotlib, and seaborn whether you want to use or not if we can see later. As usual, I want to print out the different version of the libraries. This is to ensure that if you say that your code runs and your friend has written the same code, but that doesn't run, so you can verify that the library versions are the same or not. We will be first looking at a spreadsheet. These are some randomly generated names and marks across 3 different subjects, math, science, and economics of 20 students. So we have the data in a spreadsheet, which is a very natural format to store such data. But previously, we have looked at numpy. So we want to see that if we can use numpy for analysis of this kind of a data. So if we were to do that, I would want to load the data in numpy. So I've also saved the data as a CSV file. And a CSV file is something like this. This is how a CSV file looks like, comma, separated values. You have the values which are separated by commas. So you can use this format and you can load this data in numpy. You can load a file in numpy using numpy.load.txt. You have to give something known as a delimiter, which is what the values are being separated by. We're skipping out the first row because we don't want the header to be considered a part of the data set. And we have kept the data type to be string. Any reason why we have kept the data type to be string? We have data which is string plus we have numeric data. So initially we are keeping everything as string, and later on these columns corresponding to maths marks, the science marks, and the economics marks, we will convert them to integers. So that is the strategy we will be using. So you can look at this function np.load.txt, and if we do this, if we call this function, we get a data set looking like this. Now if we print out the type of the data, it is this angle bracket U9. Any thoughts as to what this U9 might mean? So the other data types that we have seen are integers, float, complex numbers. What do you think U9 might mean? It is corresponding to a string. And can you think what the number 9 means? Length of the longest name. I think this particular name is of 9 characters, so therefore they have allocated 9. Maximum string length they have allocated. Now once we have this, we want to somehow do some analysis on this, like figure out what is the mean marks in mathematics, what is the mean marks in science, so on and so forth. If we have to answer such questions, we want the data type to be converted into integers or floats. Because we don't want them to be as strings, we cannot do any operations on them. So this is how we used to access the first column, if you remember. Select all the rows and select the first column from data. We're converting that to list, not necessarily needed. Maths NP, we take all the rows, first column, we save that as an numpy array of type integer. Similarly with science and similarly with economics, we do this. After we have done this, now we have the math NP, science NP, and eco NP. As if we look at the type of these, it's a numpy.nd array. And if we look at the if we want to look at the D type, it's in 64. It's no longer a float. So therefore, now we can do some analysis on top of this. So let's say if we wanted to figure out the mean marks in math and science and economics, we just can call np.mean. And in this cell, we can then print out the marks. The mean marks seems to be 73.85, 73.65, and 80.15. If you've not seen this earlier, this is known as F string formatting. You might have seen this earlier in the Introduction to Programming course. It's a very convenient way of writing various variables within a string. We could have written it in other ways also, which Python loves. And this is telling you that the formatting has to be with floating point with 3 decimal places. That's what 0.3f means. You could have also tried with some integer formatting if you wanted. Let's say if I told this is an integer and I were to give, let's see if this works or not. Okay, the D type is indeed float. Okay, so we'll have to give something on float only, but if you were to give 0.2f, you'd get to 2 decimal places. Now you can try out different questions. So one of the questions which I wanted to find was, find me the student who has the maximum marks in science. So if I go back to the spreadsheet, who has the maximum marks in science? If you look at this data, so in this it seems to be Simran or someone else. Now, if we want to run this, we can use this operator called argmax. It's a function argmax. It returns me the argument where the entry is the maximum. So it will look at science NP. It will tell me the place, the index where the value was the maximum. So if I run this, I get 18. And if I want to get the name, so I'll then go to the names array. From that, use the 18th index, and I get the name. In this case, it was Simran. So you can see that we have had to do quite a bit of things in order to find out the student who had the maximum marks in science if we are using numpy. You could have also figured out the student who had the maximum absolute marks difference between maths and science. So you can again find out the difference vector, which is the numpy.absolute value of maths minus science. And then you can find out the argmax over it. And then you can index through that identity, through that index. So in this case, you will see that the maximum gap is for the student Aryan, who had 60 in maths and 92 in science. So the gap is 32. Now you could have also used this same numpy array to produce some plots. So let's say if we wanted to make a bar plot to show the different marks for the different students. So I'll not show the entire syntax. We can cover more of this when we discuss matplotlib. But this is just to give you a sense of the amount of code you need to write. You can look at the length of the code you need to write. And you can also see that I'm calling this bar function, which means we're trying to create a bar plot where we're passing in these arrays of maths, science, and economics. And if we run this, we get plot like this. For the different students, we get the 3 different bars corresponding to their marks. Now, all of this took us a lot of time to write. And in NumPy, we saw that we had to use load.txt. We had to convert it we had to keep data type equal to string. We had to then also convert the integers back to integers. We had to do some argmax operator, then do some selection. So we had to do quite a lot of things in order to make this plot. Now we will be showing how to do the same thing in pandas. This is to just show you the capabilities, and then we'll go on and understand what are the different data structures which exist. Now, pandas provides us a very convenient function called read CSV, where you can read a comma separated values file. I just read this file, and I'm just printing it out. I'm doing this pretty print in Jupyter Notebook. So you can very clearly see that it seems now very close to what we have in the spreadsheet software. If you see, you have these indices. In this case, it's going from 2 through 21, and then you have this name, math, science, economics. Similarly, you have indices because in programming we typically start from 0 through 19, and then you have the name, math, science, economics. Importantly, if you see, the header has automatically been taken care of. So the defaults are very sensible. The header has been taken care of. And now it seems we have the data in a very convenient way in which we can do different kinds of operations. Now, a very convenient function which Pandas provides is the describe function, which will give you a very quick summary of the entire data set, of the entire data structure. It's typically called a data frame. The data structure that we use in Pandas is typically called a data frame. You get the count of 20, 20, 20 for the number of marks for math, science, and economics. For the mean, you get the different mean values, which is what we also saw previously. We also get the standard deviation across the marks, the minimum, the different percentiles, 25th, 50th, and 75, and the max marks across the 3 different subjects. So therefore, in just one function, now you can very quickly summarize the entire dataset, get a sense of the different ranges of values, you have missing values, etc. We can also, if we are typically looking at very large datasets, this is a small dataset, so we could have seen all the 20 entries. But typically we may have very large datasets, and we may want to see only the first few values in that dataset to get a sense of what it looks like. So if you saw, this is very similar to the Unix command head. This is very similar to the Unix command head, where you look at the first few entries. In the Unix command head, I think you default get 10 entries, whereas in this you default get 5 entries. But we know the way we previously probed. So I'll write head and I'll put a question mark to get more information. It tells us that this function returns the first n rows for the object based on position, and it is useful for quickly testing if object has the right type of data, etc. Now it means that the argument which is being passed as n, which is give you the first n row, the default is 5. So therefore we could have also kept n equal to 10, and you'll see the first 10 rows here. Similarly, we have a command called the tail, which will go from the other way around. It will show you the last 5 entries by default and the last n entries if you specify that argument. Now, importantly, when this data frame is constructed, it needs to store different kind of metadata or different kind of information. One, it needs to know the name of the columns, which makes it a lot more convenient than numpy. Secondly, it also needs to know this index or this row number. So the row name number is generally stored, by default is stored in a numeric range like format. So we can print this dfstudent.index. It tells us that it's a range index. So it's a range starting from 0 through 20 with a step of 1. And it also tells us the type of the columns. The columns are name, maths, science, and economics. So therefore, all of this metadata is already stored, which makes it very convenient for us. Now, let's say that, okay, first let's also see some other structure which is present. There is another function called .info. So if you call that function, you will be told about the different kind of information, specifically about the data type. Name is stored as an object, the other are stored as int64. So this is based on some automatic type inference engine which Pandas has, which will give you the different types of objects automatically. There are ways to change this, but for now we'll not bother about that. Now let's see, previously when we had to get the mean of some particular subject, so we had to then firstly figure out that in this CSV, what is maths corresponding, that's the first column, science corresponding to the second column, and economics corresponds to the third column. So we had to ourselves maintain this mapping of 1 to maths, 2 to science, and 3 to economics. But that's not typically how we look at spreadsheets. If we had to find out the mean, I would just write equal to average on this column and get the average. So therefore, pandas also is very convenient in this way. We can directly write df students and then access the maths column and call the mean function on it. So therefore, if you now note, we are trying to access a particular column by its name. Unlike previously, where we had to only access it through 0 to n minus 1 indexing. So it's a huge benefit that pandas gives us with some named access. So this particular phenomenon is known as we are naming the access. Or we're giving the column names. Previously, we had seen some plots. So we could also do those kinds of plots using pandas and in very few lines of code. Like, I can call this .plot.hist to create a histogram. Now I add 3 columns corresponding to 3 subjects. So I'll say that let me create this in a particular layout of 1 row and 3 columns. So layout equal to 1, 3. I'm giving the figure size, the bins for the histogram, and some alpha value for the transparency. Subplots equal to true, which means that I want math, science, and economics to be plotted separately, not in a same plot. So if I run this, you can note that the 3 different histograms are prepared. So using the histograms, you can get a sense of the different distributions of marks across the different subjects. Now this was 1 row and 3 columns. If I had to do 3 rows and 1 column, what do I need to change here? Layout equal to 3, 1. So if I give layout equal to 3, 1, you can now note that I get them one below the other. 3 rows, first row, second row, third row, and one below the other. This is typically very useful because now you have all of them on the common x-axis. So if you want to then compare these distributions, it's easier now, as opposed to comparing them across the different columns, where it's somewhat harder because you can't have a common reference. We could have also not used subplots and make all of them on a common plot. Here it's a little difficult to see. So we could have also then used something known as a density plot. So this is now going to show you the different distributions according to the different data sets that we have for the 3 different subjects. So now based on this, you can perhaps see that if you were to take one subject, which of them would you want to take? Math, science, or economics? Probably economics, because there the mode is known as the point where the distribution has the peak. So we study more when we study distributions, but this is the x-axis is corresponding to the marks, the y-axis is corresponding to the frequency of people getting those marks. You can see that the mark seems to be the very higher and the distribution is very skewed towards the right, compared to, let's say, science, where the distribution is generally very broad, and math seems to peak, but it's peaking around 70, 75. Now, pandas also gives you various kinds of plots. So I'm not doing a deep dive into plotting as of now. I just want to show you the capabilities and why pandas makes a lot of sense in various kinds of data analysis. So we could have also created different histograms of distributions. I'll skip these for now. And now we'll start with how to think about pandas and the 2 different data structures which are core to pandas, which are series and DataFrames. So series can be thought of as a one-dimensional array, similar to a one-dimensional numpy array, but the difference being that it is labeled. And it can be created from a Python list, numpy array, or even a dictionary. So if this is my pandas series A, B, C, D, and data is 10, 0, 50, 40. If I call this pd.series on this data, where the index is A, B, C, D, and the d type I've given to be float, so it creates this kind of a series object. Now, contrast this with a simple numpy array. So if this was a numpy array, and you wanted to tell me what is the value corresponding to C, right? How would you do that in numpy? So if you had to figure out the value corresponding to C in numpy, would you have to create two separate numpy arrays, or similar to what we previously did? You need to first figure out where C is in the labels array, get that index, get that position, corresponding to that position, then index into data. But if we have this data structure, such as pandas series, now you can correspondingly see that A corresponds to 10, B to 0, C to 50, D to 40. So it is maintaining this index along with the values. We could have also created this similar kind of a data structure. Instead of passing it to list corresponding to the data in the index, we could have created it from a key value pairs. So A is a key corresponding to value 10, B is a key corresponding to value 0, C is a key corresponding to value 50, and D is a key corresponding to value 40. This will give you the exact same kind of a data structure being created. Although in this case, the data type has been taken to be int64. In this, I had specifically mentioned the data type to be float64. So therefore, we have seen different ways of creating a pandas series. And now we'll see why it is more useful than a simple Python list or a simple numpy array, or even why it's more useful than a simple Python dictionary. If I want to get the value corresponding to C, all I have to do is to write the series name, the name of the object, and then access via the key, which is C. Right? So this is very similar to how you might have accessed from the dictionary. So if I create this dictionary, let's say I copy paste this. And if I had accesses using, you can see that the values are the same. The way to access is the same, but series will end up being much more efficient than dictionary, specifically for such structured kind of data. Because if you remember, why was NumPy more efficient than Python list? One of the core reasons was that the homogeneity of the data and the fact that many of the underlying routines are written in C. So it's a library optimized for such structured data, and similarly, pandas is very optimized for such kind of tabular data. It also allows you to do various kinds of vectorized operation. So let's say if I had to multiply each of these elements by 2, I don't have to write a for loop, which I would have had to write in a simple Python list or simple Python dictionary. I can just do ser into 2, let's say. It will then multiply each and every element by 2, which is again a very convenient kind of a function. I can sort the values. So if I sort the values, it returns me this series in the sorted way. Importantly, if you again notice, the index has been changed corresponding to the values. So it's a very convenient function. If you didn't use this, it would have been you'd have to do this in either Python dictionary or some other data structure. So it's significantly easier to do in this pandas series. 0, 10, 40, 50. Now importantly, if I print out ser, the series object, you can notice that it's unchanged. 10, 0, 50, 40. Why is this the case? When I called series.sort values, I saw 0, 10, 40, 50. But if I print series again, it is 10, 0, 50, 40. Why is this the case? Because series.sort values returns this sorted series, but it does not make the change in place. But there is another functions, ser.sort values, where if you pass in the argument in place equal to true, it will then make the changes in place And then if you were to print out the series, you'll see it's B, A, D, C, and 0, 10, 40, 50. Now previously, when I made bar plots, it was hard. I had to write quite a bit of matplotlib code, and I had to ensure that the numpy and pandas and all those things are, numpy and matplotlib interoperability is taken into care. In pandas, I just call series.plot, and I get a line plot. BADC, which is my index, comes as the x-axis, and I can see this line plot. So typically when we have the x-axis to be discrete quantities, in this case it's BADC, line plot is generally not that useful. You generally want a bar plot to show categorically distributed categorical data. So let me first show you another command. .sort index in place equal to true. Now the index in this case currently is BADC. If we have to sort the index, it will look at the alphabetical order. It will make it A, B, C, D. It will correspondingly change the values also. So if I were to now show you the series, it's A, B, C, D as the index, and the values as 10, 0, 50, 40. Now I can call this .plot kind equal to bar, and I can get this nice looking bar plot. You can again look much more into the documentation to see the different kinds of handles available. Like in this case, you can see that the labels seem to be rotated. Like we might want labels like this. Do you like these labels better? Right, they're easier to read. So therefore, there are a lot of other commands and functions and options you can read. So this is one interface. I think they also provide this interface here. I'm not sure. Yes. So they also provide this interface. .plot .bar. Give the plot type directly, or .plot and give the kind equal to the bar plot, and then rotation equal to 0. Because there are a lot of options, you can just try and see different options by looking at the documentation, or just give series.plot question mark. It will show you the different kinds of plots available. Another important type is the horizontal bar. So in this case, you can see A, B, C, D. Instead of the vertical bar plot, you get a horizontal bar plot. Now, I showed the accessing of the value by using this index value C, and I got the value 50. But let's say if I had to use the older index or the position based indexing, I could also use that. So let's say I want to access like a numpy array. I want to get the value at position 2. I would give this iloc. So whenever you see this I in pandas, it generally means you're doing a position by indexing. So iloc of 2, it will give me the value corresponding to the second position. So if we print out, so 0th position, first position, second position. So if I look at .iloc of 2, it gives me the value corresponding to location by position 2. We have already seen that the generally more convenient way of accessing the values is by using the index. So ser.loc of C, you're trying to find out the value corresponding to the location of the index C. So previously I had done this way, and you can notice that you get the same thing. I would recommend to make it more consistent and see if you can just use .loc everywhere. This is more convenient often, but you can always just use this to make it very clear exactly what you're doing. Okay, here I was showing the different ways of accessing, and you get the same value. You could have also tried to get now let's say the values corresponding to some indices, a range of indices, like we did in numpy. So I can say that give me the locations corresponding to the positions 1 through 3. So it will 1 through 3 will do for 1 and 2, not include 3. So it always starts from the first position, goes till n minus 1, where n is given as the stop positions. This is a slicing in Python list, similar in numpy arrays and similar in pandas. We could have interestingly also tried to access it. So more natural way might have been to give me all the values from B through D instead of from position 1 through 3. So that is also possible. I give dot lock and I give B through D. Importantly, if you notice the difference, in this case, it is also including the value corresponding to D. Whereas in this, when I was giving the iloc from 1 through 3, this went from 1 till 3 minus 1. So those are the values returned. But if I were to give dot location B through D, I get the B, C, D, all the values. So small caveat, you should be very careful about this. Like with pandas, they also have this nice functionality for describe method, which is a very quick summary. I very often use this describe method to very quickly get a sense of the data set that we have. You can call dot mean to get the mean of the entire data frame. And you notice that this seems to be in some containerized structure. This is some 25.0, but contained in some numpy.float 24, float 64. So we can also, let's try and print this to show you the difference between the two things. This is what you have. This is the nice, convenient way to print. Let's also see the type. So this seems to be a numpy.float64. I can also do series.mean.item and print the type of it. Can you see the difference between these two? This is just a float, and this is a container containing this numpy container containing the value of 25.0. So small thing, but you should be careful when you are looking at the different data types. They also provide a very nice function for ranking. So the values, if we print out the series again, the lowest value corresponds to B, so it gets the rank 1. The second lowest value corresponds to A, so therefore it gets the rank 2. The third lowest should be D, so it gets the rank 3, and the fourth lowest would be C. So therefore you can see this ranking. It's very often useful when you're trying to sort some data, get some sense of the top K entries in the data frame. Now sometimes we want to see the values of the pandas series in a numpy array. So you can see that the interconversion is very nice. You can call this dot values on the series, and you can see that I get this values 10, 0, 50, 40, and the type of them is numpy array. So therefore you can see the nice interplay between numpy arrays and the pandas series. The pandas series can contain numpy arrays as the set of values and the set of indices also. Now in numpy we gave you this question of trying to do some masking, trying to figure out some set of values which are greater than or less than some values. This is also quite easy in pandas. So let's say I wanted to figure out the values which are greater than 20. So firstly, I can do a binary masking. If my series is like this, 10, 0, 50, 40, you can see that it should return a true only corresponding to C and D. So C and D, it returns a true. For A and B, it returns a false. So again, a very natural way of running this masking. And now if I do series of this mask, I can also do mask equal to this. And I put this mask So now I've returned another series with a subset of the entries, in this case only C and D, and corresponding to them the values. It's very useful for filtering different kinds of data, doing different kinds of data analysis. Now this was a one-dimensional data structure corresponding to a unidimensional numpy array, but importantly it has the index also, which a numpy array does not have, so therefore you have to necessarily their index by the position. Similar to this, now we have the two-dimensional tabular data structure. Whenever I talk about data frame, I want you to picture in your head something like a spreadsheet. You have the different columns, you have the index. Right? So I'll create this simple data structure using, in this case, a Python dictionary. I am given the names, 3 names, values of age corresponding to 3 entries, and similarly 3 scores. If I just call a pd.DataFrame on this dictionary, it creates me this nice data structure very quickly. Now, importantly, you can again see that the index is going from 0, 1 through 2. The name is a column, the age is a column, the score is a column. We may also have done something else here. Okay, so if we copy this, I don't know whether this will work or not. Let's try. No, we can't give it this way. So we can't give an index column here. Okay, so first let's just create this data frame. Okay. And now this name is repeated. I can also then just do a drop. Okay, so I think I'm making a mistake. Do I need to give a list? No. So how do we drop columns? Okay, we needed to give the axis 1 for the columns. Right, so now you can see a different kind of a data frame. Previously you had a data frame like this, where it was indexed was 0, 1, 2, and you had the columns name, age, score. But you can also create a separate kind of a data frame using the same data set, where the name becomes the index and the age and the score become the columns. Now we look at, once we have these kind of data frames, so this was your data frame. Now, we've seen this earlier. The different plot functionalities exist. So you can print the age and the score corresponding to the 3 different users. So it's a very convenient way of writing this. Had you had to do this in NumPy, this would be much more lines of code. Now, once we have created this data frame, we also have different kinds of indexing selection which make the whole process much more useful for data analysis and exploration. So let's see another different data frame. Here I've randomly created 5 values for X, 5 values for Y, and I've created 5 integer values, which are integers from 1 through 10. And I've explicitly created an index, which is A, B, C, D, E. So after this, you can see that the data frame has the index A through E and the columns X, Y, Z. For some reasons, the cells disappear. Okay, you can see the description of these also. Now, our data frame has the index which is A through E and the columns X, Y, Z. We can see this. If we have to select a specific column, we can just give the name of the data frame and then the name of the column. So it's a very convenient kind of an access. Just give this label Y and I can get this thing. What do you think is this returned object data type? Is it a list? Is it a dictionary? Is it a pandas series? Is it a pandas data frame? It's a pandas series. You should always try and verify these things also. So if I do type of df2.y, it is a pandas.co.series.series. So therefore you can see that a data frame is consisting of multiple series. Each series is having the same index. You can also think of a data frame to be considered in that way. As previously shown, we can also use the .loc method. So .loc accessor and then give the row name to get the values corresponding to the cth row. So now this gives you values corresponding to 3 columns. We could have instead also used iloc. Iloc will be position based indexing. So if I want to get the values at position 2, which is corresponding to C only, which is the same. So both of these are giving you the same value. Just that accessing it via the index name is much more convenient as opposed to indexing it via the iloc method. Now, again, if we start combining various functionalities which we've learned earlier, so we can do simple masking. We can check the values where z is greater than 5. You can notice that 3 of the rows have z greater than 5. So we can create a mask where the df2 of z is greater than 5. And then if you put that mask as the accessor, as the selector on the df2, we get these different rows. You can notice that the index has been accordingly just chosen corresponding to the values where z was greater than 5. Now we can also extend this .location access to select both rows and columns. Yes. So we have to access the entries corresponding to the cth row and one of the columns. So we can do it by this. We call the .location, .loc, the row, and then you comma the column, which would correspond to df2.iloc of 2, 1. You can notice that both of them give us the same things. Now we can also extend this further. Here we were doing a single entry. We're trying to figure out a value corresponding to a single row and a single column. But we can extend this further. Let's say if I want to find out the values corresponding to row A and C, so within .loc, I can pass in a sequence of rows, not just a single row. So I can give this A, comma C as a list, and it will give me the rows, the values corresponding to the rows A and C. What if I want to then also select columns X and Z? So I could have done it using df2 and then given this columns, list of columns X and Z. It will return me two set of values. So it will return me the 5 rows and corresponding to the 2 columns. Or you could have just used the .loc method where I access all the rows. This is similar to the numpy notation which we used. Colon means select everything. Comma, in this case it's rows, and then comma columns. So when you give the comma, after that if you give in the list of the columns which you want, list of the columns you want is X and Z. So df2.loc all rows, comma, columns X and Z. It gives you this particular way. Now you can combine all of these, and let's say if you want to print out select rows B and D and columns X and Z. So we could do df2 dot selection for the location corresponding to the rows first. We want for B and D. So let me first rows to select is equal to B and D, and calls to select them be X and Z. So you can see that now I am returning the rows B and D and the columns X and Z using a single one line. I would recommend you to mostly try to use this notation, because in a single notation you can do various kinds of things. You could have also done something like df2.loc of for the row selector. I don't know whether this will work or not, but let's try. Okay, so this would work. Now let's try and do some column selector also. Okay, this works. So this, you can specify the ranges also, which makes it again very convenient to do this selection. Now very often we are given data frames where we have to do some manipulation by combining different data frames, merging, joining. There are different kinds of operations. So therefore there are very nice convenient utilities already provided, such as concatenation to stack different data frames either row wise or column wise, .append, which is similar, and .merge, which is more like a database style merge. I believe you have not yet studied databases. A very small subset of you might have studied databases in your class 11th and 12th, where you have studied SQL. So it's similar to that. Let me first show you the different data frames. You have the first data frame X, which has the index 0, 1 and the 2 columns A and B. And similarly, you have the data frame Y, which has the index 0, 1 and the columns A and B. Now so we have specifically kept them A0, B0, A1, B1 and A2, B2, A3, B3. If we call pd.concat X, comma Y, it creates this bigger data frame where the index seems to be a bit weird now, if you notice. 0, 1, 0, 1, and the columns are A and B. So if this is our df dot concatenated data frame. Now if I try to access corresponding to my index 0, what do you think will happen? What should happen if I give df concat.log 0? No answers? So there are only 2-3 options you can get. One, you might think that it will return both these rows. The second is that it may want it to be selecting the index has to be unique, so therefore it might not be able to give you anything. So let's try and run this. This case, if you notice, it gives me both the entries. Right, so it could have been either an error or it returns both the entries corresponding to the index being 0. So therefore, typically when we're doing such kinds of concatenations, we may want to say that ignore the index. So it will then create a new index starting from 0 to something. So if we do it this way, now if we were to access via index 0, it will ensure that you get a single row. There are different things you may want to try here. So what if this index instead of 0, 1 was 2 and 3. And then if you were to do the concatenation, will you get 2, 3, 2, 3? Or whether you'll get 2, 3, 0, 1? Or whether you'll still get 0, 1, 2, 3? There are a few things you have to try and understand the API a bit more. Now in this case, the two data frames were put one below the other, which is we were doing row-based stacking. We could also do column-based stacking, where the index will remain the same, but we'll have 2 additional columns. So we could have also done something like, if we have the first data frame to be AB, the second data frame to be having columns CD with the same index, and if we were to do this concatenation, you'll notice that now the concatenated data frame looks like the columns have A, B, C, D, and we have 2 rows corresponding to the index 0 and 1, and then we have the 4 entries. Now to understand merges, let's look at this data set, which is provided in Seaborn's tip data set. This is talking about the different tips people may give on when they're going to different kinds of restaurants. So the data frame looks like this. We'll create some additional rows on our own so we'll create another table. So typically when we talk about merging, we are talking about 2 different tables which exist, and we want to merge the information from both the tables into a common data frame. So you have one tips data set containing this kind of a data set, and let's say we created another table which just contains the data about the customer ID and whether they are VIP or not. So I'm just artificially trying to create this. And I'll also attach the customer ID in the previous database. So now think of this as you have 2 different data sets, one containing the tips information and the customer ID, the other containing the customer ID and whether or not they are VIP. It's very often a practice that people end up creating these different kinds of tables where they store the different kinds of informations. Now, when you want to do some analysis, you may want to ensure that you may want to do an analysis across both these tables. So, if you notice that this table has customer ID going starting from 119, 148 to 84 and on. This one has customer ID going in from 32, 22, 136, 137. So both of them are not in sync, but the customer IDs in both of them are the same. Right? So therefore, you may want to do something known as a merge operation, where you'll say that I'm merging the 2 tables on the customer ID field, and then you'll have created a table something like this. Right? This will ensure that the columns have been synced up the two tables have been synced up according to the customer ID. So it will look up customer ID equal to 32 in both the tables and put all of their values together. That's the simplest definition of what a merge is. If you notice that both the tables had 244 rows, the first one had 2 columns, this one had 244 rows, 8 columns. On merging, we have 244 rows and 9 columns. Now you can do various kinds of analysis on this data frame to try and understand that are VIPs tipping more, are VIPs eating more at any particular time of the day or not. And in order to do this kind of an analysis, we very often require some kind of grouping and aggregation. So it's a very common paradigm in pandas. So this particular paradigm is known as GroupBy, where you split the data as per the different groups. You apply a function to the groups separately, and then you combine the data, the information into some data structure. So we have already looked at a few examples of grouping when we looked at in the first lecture. Let's say we were trying to look at when we were trying to understand the Simpson's paradox. We looked at the different groupings of, let's say, college admissions by gender, or we were looking at the different flowers by the species. So in all of them, we typically need these group by operations. So first, let's say that someone asks you, given this data set, can you tell me which day of the week do we get the maximum tip? How would you go about answering such a question? Which day of the week gets the maximum tip? Firstly, do you need to firstly know what are the different days present in the data set? Yes? Once we have the different days present in the data set, can we loop over those selected days and then find the mean over them, the different groups? So I can call this tips.location accessor, all the rows and the day column. This tells me there are 244 records. Now pandas has nicely already shown that this data is stored in a categorical data type. So therefore it shows that there are 4 different days: Thursday, Friday, Saturday, and Sunday. Now we can also call this nice convenient function .value counts on this accessed day column. So it tells us that the number of records are Saturday, Sunday more, Thursday and Friday are lesser. So it probably suggests that their business gets more visitors on Saturday, Sunday compared to Thursday and Friday, which is perhaps obvious. Now we could have also called this function .unique to find out the unique days in the data set. So this is Sunday, Saturday, Thursday, and Friday. Now let's say that I want to access the rows corresponding to only the unique set of only those specific days. So let's say if I want to get the data frame where the day is Sunday, so I'll call tips of day equal to Sunday. If I do that, I'll get a binary mask of length 244. This was also one of the questions asked in the doubts and clarification channel. The mask is of the same length. When you apply that mask on the object, you get a subselected set of data frame or a subselected numpy array. So if I apply this mask on tips, I look at the tip and look at the mean of it. Sorry, let me run this again. This is giving me the mean tip or the average tip that we have received on a Sunday. Right, so we can do all of this manipulation. We can also write a for loop for this. We create an empty dictionary out equal to, this is a very common paradigm which I use and people use with pandas.Series and DataFrames. You find out the day in unique days. So day in unique days means the day can be Saturday, Sunday, Thursday, and Friday. You create a mask corresponding to that day, and then out of day, so this is storing the mean tip received on that particular day. And this is the dictionary. I can conveniently create a pandas series around it, and I can then do some plotting around it. Right, so I could have done then series.plot kind equal to bar to look at the different days, and maybe it shows that Sunday and Saturday have much more tips. Now, all of this required us to write multiple for loops. If you have to write a lot of for loops in NumPy and Pandas, it means you're not doing something perfectly. Oftentimes, you can get away with for loops by using some inbuilt constructs. In NumPy, we were looking at broadcasting-like things. In Pandas, if we have to categorize the data, we should not be using for loops. Instead, we should be calling something known as the GroupBy operation. So this is the data frame. I want to group the data by the column day, and I want to get the tip value. So this gives me a GroupBy object, and I call the dot mean function on it. So therefore, now in just a couple of lines of code, I get the same value which I got previously. Thursday 2.7, Friday 2.73, Saturday 2.9, and Sunday 3.25. 2.7, 2.73, 2.9, and 3.25. You can see that we get the same set of values, but this is just a lot more convenient. But we should not just be ending here. So we were only looking at the mean. Perhaps we also want to look at the count, the sum, the mean, and the standard deviation of the entries across the different groups. So therefore, we can again use the same GroupBy object, tip.GroupBy day observed equal to true tip. We want to get the tip out of it. And then do the aggregation via the count, sum, mean, and standard deviation. So it gives us a very nice, convenient data frame. It tells us that the number of people who tip on Thursday is 62. The sum of the tips is this, the mean of the tips is this, the standard deviation is this. So standard deviation is often very useful to understand the difference between the different groups. Now, in this case, we were grouping by a single value, single variable, which was the day. We can also group by different things, not by a single variable. Let's say we want to group by the day and the time. We want to very precisely understand and explore a data set that during which time do we get more tips. Is it Thursday? Are the different lunches and dinners contributing differently in tips, or is it the same across all of the different meal times? So in this case, you can very clearly see that if we didn't do this analysis, we might have said that Friday is a very dull day, but Friday dinner gets a lot of tips compared to Friday lunch. So perhaps they need to figure out that why does Friday lunch fetch them very low tips. So this is the kind of data analysis they need to do in order to understand the different kinds of exploration they're trying to do. Finally, there is another very convenient function called the pivot table, which can very nicely summarize different kinds of data frames, as we also do in spreadsheets. So Excel also has this pivot table functionality. We can search for it, Excel. So they have this functionality to analyze the worksheet table data. You can study more on this, but I'll just show one simple example. I wanted to store values in this data frame corresponding to the tips. I want the index to be my day. My index is my day. I want the columns to be the time, which is lunch, dinner. I want to do my aggregation over the mean, and then I am providing some other arguments which you can study. So this has very nicely, very conveniently created this entire data frame for me, which is showing me the lunch, dinner and all, and it is also showing me corresponding to the different times. Now you can notice that there are these entries called NAN, which correspond to not a number, which means that there is no entry found for Saturday lunch and Sunday lunch. We could have also filled these with zeros. We could have filled them with zeros, or we could have thrown away the entries where we have a single, not a number. So we can do that by calling something known as drop NA. Drop NANs, drop the values where we don't have the data. Pandas also provides this very nice functionality for string operations. So for example, if this is our original pandas series, hello world and Python 3.9 pandas school, so on and so forth, we may want to ensure some consistency, which is we may want to ensure that everything is in lower characters, and we want to remove different kinds of extra spacings. So if we call this on pandas.Series, so we have to call it .str method to access the strings. And if we then clean it, you can notice that it's done a bunch of those cleaning things. It's very convenient when you're trying to, let's say, do some data analysis. You want the data is not in a clean way. There are missing values, there are some spaces, it's not consistent. So therefore such things are useful. The string operations also provides you to other utility methods such as .contains to figure out which of them contains Python. So we can very conveniently run this, and then based on that, we can do some selection, we can do some masking. We can also do some replacement, replacing small is with capital Is, and so on. Finally, I want to show you if you have to create some additional columns in the data frame. So let's say if this is your data frame, it contains columns A, B, and D, A, B, and C. Let's say we want to create another column D, which is the sum of A, B, and C. So they very nicely provide this function.eval, where the new column D is created, which is A plus B into C. So you can do some very fancy things here. In place equal to true, and after we have done this, it will create this new column. Now, so when I teach machine learning, I also use the same kind of function to evaluate something known as the entropy function. So the entropy function is summation p log p, where p is the probability of yes and no of the different classes. So therefore, if such functions exist, we can very nicely, conveniently create a new column where we combine the different columns in a different way, in any specific mathematical way. Finally, the query function. So the query function is where we want to query a subset of the rows on some condition. So let's say I want to query the rows for which d greater than 0, I can very conveniently do df eval.query and give the specific condition in string. Now there can be some corner cases in this where you have to figure out how to do some different kinds of operations. Let's say in this case it was specific to 0. What if this was the variable? What if this was evaluate or query the objects based on the values which are greater than the mean? So you cannot write d.mean here. You'll have to have some other accessor to mention that you are selecting the mean. So this was about some different functionality in pandas, which will enable you to do a lot of data analysis.